Good morning. NMR is a type of spectrophotometer. So we've used visible light absorbance spectrometers already in this lab. And we can use different parts of the electromagnetic spectrum to learn different things about molecules. So the absorbance spectrometers that use visible or UV light, which is sort of what we've done before, have a tendency to explore and quantify compounds with color. In the NMR, we happen to use the radio frequency range of the electromagnetic spectrum. And instead of little cuvettes, little square cuvettes or test tubes, we'll use glass tubes that look like this. And the shape is somewhat useful. I mean, it's why there's a reason for it. But NMR has sort of unique history. It's been around for decades, but it actually was the technology that evolved into the modern day MRI device, imaging devices for people. So if you can picture an MRI with a big loud magnet and an opening in the center, round opening that a person slides into, well, ours is basically a small version of that with a very small opening that our small narrow sample goes into. But we wanted to give you with this video a little bit of background of sort of the theory, what's going on in the instrument, so that in lab we can focus a little more on the material and try and interpret the data. Radio frequency, that part of the electromagnetic spectrum, has enough energy to cause the nuclei of an atom to flip their spin orientation. So to kind of put it in perspective, UV light, which is pretty high energy, has enough energy to maybe ionize or eject electrons from an atom. The visible light has enough energy to cause electrons to become excited to higher state orbitals, and they can relax, and so you see effects of color, absorbed light and emitted light. And you can go all the way through the spectrum and you learn different things about the molecule, because different parts of the electromagnetic spectrum have energies that can let you cause different interactions or different perturbations in the molecule. Infrared light doesn't cause electrons to become excited into new orbitals, but it does cause bonds to vibrate. So you can learn something about bonding, and also a very good tool to identify molecules. Anyhow, but if we get to the radio frequency range, RF, that's what we're using in NMR, can cause the nuclei of atoms to flip their spin orientation. So the nuclei, if you imagine that nuclei are filled with protons, so we'll give you sort of a general description. Nuclei are filled with protons, they have charges, and if they're spinning, it creates an electromagnetic field. For the most part, your atoms, so think of your body, all of your atoms have nuclei that are spinning and rotating. They all have little electromagnetic fields, and they're all kind of interacting with each other. But if you were to try to figure out which direction are they all pointing, they would, for the most part, look a little bit random. But if we could put you inside a very high-powered magnet, this is what happens in the MRI. The large magnet has a big, powerful magnetic field. All these little atoms, all the nuclei, have their own electromagnetic fields, and they'll all line up. And so inside an MRI, although you don't feel it, doesn't feel painful at all of your nuclei are actually pointed and spinning the same direction, which is pretty incredible to think about. So in our experiment, you're going to have a sample in one of these tubes. It's going to go into what looks like a big box, but trust us, inside this big box is a very powerful magnet. And all of the nuclei that were somewhat randomly spinning around are actually all going to line up with the magnetic field. That is the way they want to orient inside an external magnetic field. And so this is what we call the ground state. This is the lowest energy. It is what it wants to do at under these conditions. So all the nuclei are going to be lined up. Then, if we irradiate the sample with radio frequency radiation, we give it enough and just the right energy, these nuclei can absorb that energy and flip. And now they're spinning opposite the big powerful magnetic field. And this is the excited state. So we have ground state and excited state. If we pull the radio frequency away, so we turn it off, all the nuclei that were excited and fighting against the NMR magnet, they're all going to flip back. And if you turn on and off the radio frequency pulse, you get the nuclei flipping back and forth. Now, since you have ground state and excited state, there's a difference in energy, there's absorption, there's also emission. And most of the modern NMRs, and ours, an FT, which stands for Fourier transform, but an FT NMR, they really function as an emission instrument. So we use a pulse of radio frequency to cause all of the nuclei to be in the excited state, so they're opposite the magnetic field. Then you pull it away, so it's going to turn off, and then all these nuclei flip back. And when they flip back, they're going to emit radio frequency, but that radio frequency is unique to that type of nucleus in that environment. So we get this spectrum. The spectrum is produced, and we'll maybe try drawing a few of these, and that's a lot of what we're trying to do in lab. Those, the x-axis is essentially frequency or energy, and we're going to see peaks at different places. Where they show up tells us a little bit about the identity of that atom. And for the most part, NMR can give us a unique identification for the molecules.